the Boeing B-17 Flying Fortress. Even the name sounds indestructible. It was America's pride, the plane that won the daylight bombing war over Europe. 4 engines, 13 guns, a fortress in the sky. But in early 1943, there was another bomber flying alongside it, the Consolidated B-24 Liberator. It carried more bombs, flew faster, and went farther than the fortress. On paper, it was the superior machine. But the crews who flew it, the men who climbed into that aluminum tube every morning knowing they might not come home, they called it something else. They called it the flying coffin, because when German 88mm flak shells exploded near a B-24's wing, something terrible happened. The wing didn't just get damaged, it cracked, it shattered. The entire outer wing panel would fold upward like a bird's broken wing, and 22,000 pounds of airplane, fuel, bombs, and 10 human beings would tumble out of the sky in a flat spin. No parachutes, no time, just a smoking hole in a French wheat field and 10 more telegrams going home. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. By March of 1943, the 8th Air Force had lost 47 B-24 seconds this way, 47 planes, 470 men. The Boeing Fortress flying right next to them through the same flak field would come home with holes you could stick your fist through, but the wings stayed on. The Liberator's wings just snapped. The Army Air Force was in a panic. They grounded inspection teams. They X-rayed wing spars. They tested metal samples. Everything was within specification. The aluminum was good. The rivets were good. The design was approved by the best aeronautical engineers in the country. And yet, men kept dying. This is the story of one man. A 38-year-old machinist from Detroit named Frank Piasecki, who had never finished high school, who'd spent 20 years building cars on the assembly line, and who solved the problem that MIT-trained engineers couldn't see. But he didn't make the wings stronger. That's what everyone expected. Instead, he made them weaker. He made them flex. And that stupid, backwards idea that violated every rule in the book saved over 1,100 American lives. To understand what Piasecki was fighting, you need to understand the enemy. Not the Luftwaffe, the Flak, Fluggewehrkanone, aircraft defense cannon. The Germans called it 88, 88mm. To the American bomber crews, it was just hell. A German 88 crew could fire 15 rounds per minute. Each shell climbed to 25,000 feet in 11 seconds. The fuse was set before firing, timed to detonate at the exact altitude the bombers were flying. When it exploded, it didn't need a direct hit. The shell fragmented into 1,100 pieces of white-hot steel, shrapnel moving at 4,000 feet per second. A single airburst could shred everything within a 70-foot radius. The sound, the crews said, was like someone hitting your airplane with a sledgehammer. Then, the concussion wave. It was an invisible fist of compressed air that slammed into the aircraft at the speed of sound. It rattled your teeth. It blurred your vision. It felt, one navigator wrote, like the hand of God trying to swat you out of the sky. Now, picture this. March 19th, 1943. A B-24 named Lucky Strike from the 93rd Bomb Group is on a mission to hit the submarine pens at Saint-Nazaire, France. They're at 22,000 feet, in tight formation, 21 bombers stacked in a combat box. The flak starts at the initial point, 10 miles from the target. Black puffs appearing in the blue sky like evil flowers. The first burst is 200 feet low. The crew hears it. Whomp. A dull thump. The plane shudders. The pilot, Captain Howard Bressler from Pennsylvania, holds the formation. He has to. If he breaks, The whole group's bombing accuracy goes to hell. The bombardier, Lieutenant Kenneth Wade, is lying on his stomach in the nose, eye pressed to the Norden bomb site. He's counting down. 2 minutes to target, steady. The flak is getting closer. Whump, whump, whump. 2 bursts, 1 on each side. Shrapnel punches through the aluminum skin of the fuselage. A piece the size of a quarter slices through the radio operator's desk. He's not hit. Pure luck. 1 minute to target. The German gunners have the altitude now. The next burst is close. 20 feet off the right wingtip. The concussion wave hits the plane like a freight train. The B-24 lurches. Every man on board feels it in his gut. Bressler fights the controls. The yoke is shaking in his hands. He glances out at the right wing. He can see daylight through 6 new holes in the metal skin. But the wing is holding. 30 seconds. Wade's voice on the intercom. Steady, steady. Bombs away. The plane lifts as 6,000 pounds of high explosive drops free. Bressler banks left, away from the target, away from the flak. He's climbing now, trying to get altitude. The formation is spreading out. Every pilot desperate to get away from Saint-Nazaire. And then, at 23,000 feet, 5 miles from the target, 1 more burst. 1 last 88 shell. It detonates 30 feet below Lucky Strike's right wing. The shrapnel doesn't hit the wing. It doesn't have to. The concussion wave, that invisible sledgehammer, slams upward into the wing structure. It hits the main spar at the point where the outer wing panel connects to the center section. The spar is a massive I-beam of aluminum alloy, 7 inches tall, 3/8 of an inch thick. It's designed to carry 60,000 pounds of bending load. It's been tested. It's been approved. And in that one instant, it cracks. Not a clean break, a fracture, a hairline split that runs 18 inches along the lower cap of the spar. Bressler doesn't know it's there. He can't see it. The crack is inside the wing, hidden under the skin. But the wing knows. The structure is compromised. And now, every vibration, every gust of wind, every bit of turbulence is working that crack, spreading it, atom by atom, rivet by rivet. Lucky Strike is a dead plane flying. The crew doesn't know it yet. Bressler is flying straight and level. The engines are running smooth. Oil pressure good. Fuel flow good. Everything seems fine. 10 minutes pass. The formation is over the channel now, heading home to England. The waist gunner, Sergeant Paul DeLuca from Brooklyn, is checking for damage. He sees the holes in the fuselage. He sees hydraulic fluid leaking from a severed line. He's writing it all down on his damage report form. Normal battle damage, repairable. Then, at 23,000 feet over the English Channel, Lucky Strike's right wing folds upward. It happens in less than 2 seconds. The outer wing panel, from the number 3 engine to the wingtip, bends up 30 degrees. The main spar, already cracked, snaps completely. The ribs buckle. The skin tears open like paper. The aircraft rolls violently to the right. Bressler is thrown against his harness. The control yoke is useless. He's pulling with everything he has, but the ailerons on the left wing can't overcome the massive drag of the broken right wing. Lucky Strike enters a flat spin. At 23,000 feet, spinning at 180 revolutions per minute, the crew has maybe 90 seconds before impact. 90 seconds to get out. The bomb bay is jammed. The waist door is blocked by the centrifugal force. 2 men, the bombardier and the navigator, manage to bail out through the nose hatch. They pull their ripcords, their parachutes open. They survive. The other 8 men, including Captain Bressler, ride Lucky Strike down. The bomber hits the water 7 miles off the coast of Dover at 400 miles per hour. The impact disintegrates the aircraft. There's nothing left but floating debris and an oil slick. The British Air Sea Rescue launches a boat. They find the two survivors, Wade and the navigator, Lieutenant Frank Morrison. They find pieces of the airplane. They find one body, the radio operator, still strapped into his seat. The other 7 are never recovered. The official report, filed 3 days later, lists the cause as structural failure, right wing, due to enemy action. No blame, no fault, just another statistic. But lucky strike was the 9th B-24 to go down this way in March alone. 9 aircraft, 90 men. The pattern was undeniable. The problem was in the wing. And back at the Consolidated Aircraft Factory in San Diego, California, 7,000 miles from the war, the engineers were tearing their hair out. The B-24 Liberator was a triumph of modern engineering. It was designed in 1939 by a team led by Isaac M. Ladden, one of the finest aeronautical engineers in America. The wing was a masterpiece. It was a high aspect ratio, Davis airfoil design. It was thin, efficient, and gave the Liberator its long range and high cruise speed. The wing was built in 5 sections. A massive center section that ran through the fuselage, bolted directly to the main frame, and 2 outer panels on each side, attached at a structural joint 17 feet from the center line. The main spar, the backbone of the wing, was a monster. It was an I-beam made of 24ST aluminum alloy, heat-treated for maximum strength. The lower cap of that spar carried the primary tensile load, the force trying to pull the wing off the airplane when it was loaded with fuel, bombs, and the stress of flight. The engineers at Consolidated had calculated every load. They'd tested the wing to destruction in the factory. They'd loaded it with sandbags, simulating 60,000 pounds of force. The wing held. It passed every test. And yet, in combat, it was failing. The fractures were always in the same place. The lower cap of the main spar, 18 to 24 inches outboard of the wing joint. The Consolidated engineers couldn't understand it. They brought in metallurgists. They X-rayed the aluminum. They checked for impurities. Nothing. The metal was perfect. They checked the rivet installation. Every rivet was countersunk, driven to spec, and inspected. Perfect. They checked the heat treatment. Perfect. They even brought in a stress analyst from Caltech, a man with a PhD in structural mechanics. He reviewed the calculations. He ran the numbers again. On paper, the wing should never fail. But in the air, in combat, it was failing. The problem landed on the desk of a man who shouldn't have been there at all. His name was Frank Piasecki. He wasn't an engineer. He was a shop foreman. He'd been hired by Consolidated in 1941 to supervise the rivet crews on the wing assembly line. Before the war, he'd worked for 20 years at the Ford Motor Company in Detroit, building cars. He'd started on the line, driving rivets into Model T frames when he was 16 years old. He'd worked his way up, not through college, through sweat and common sense. Piasecki understood metal, not from textbooks, from touch. He could look at a rivet and tell you if it was driven right. He could hear the difference between a tight joint and a loose one. He could feel, with his fingers, if a panel was stressed. It was an instinct, a craftsman's knowledge that no degree could teach. And in March of 1943, Frank Piasecki was standing on the wing assembly line at Consolidated's San Diego plant, watching his crew install the lower wing skin panels on a B-24 when he saw something that bothered him. The rivets were too close together. The specifications called for rivets every 1.5 inches along the spar cap. That was standard aerospace practice. Tight rivet spacing meant a strong joint. It was in every engineering manual. But Piasecki, looking at the joint, thought it looked wrong. He couldn't explain why. It just felt wrong. He'd built enough cars, enough frames, enough stressed structures to know that sometimes tight isn't strong. Sometimes tight is brittle. He went to the engineering office. He found the lead structural engineer, a man named Donald Palmer, a graduate of MIT, sitting at his desk surrounded by blueprints and slide rules. Piasecki knocked. Palmer looked up. He saw a shop foreman in greasy coveralls, a man who smelled like cutting oil and aluminum dust. Palmer was polite, but dismissive. "What can I do for you, Frank?" Piasecki, hat in his hands, explained. He said the rivet spacing on the lower spar cap, "It's too tight." "The specifications," he said, "are based on accepted engineering practice. Tight rivet spacing distributes the load more evenly." Piasecki tried to explain. "In a car frame," he said, "we space rivets farther apart. It lets the metal flex. If you lock it down too tight, it can't move. It cracks." Palmer's expression hardened. "Frank," he said, "this isn't a car frame. This is an aircraft wing. It's under entirely different loads. The calculations are sound." Piasecki pushed back. "With respect, sir, have you ever driven a rivet?" Palmer stared at him. That question, that simple question, ended the conversation. "No, Frank," Palmer said coldly. "I'm an engineer. I design structures. I don't build them." Piasecki nodded. He understood. The conversation was over. He was a machinist. Palmer was an engineer. Palmer had a degree. Piasecki had grease under his fingernails. But Piasecki couldn't let it go. That night, he went back to the factory floor after his shift ended. The plant was quiet. The swing shift was working on fuselage assembly in another building. The wing line was empty. He walked down the line, looking at the wings in various stages of assembly. He stopped at a wing that was nearly complete, the skin panels installed, the rivets driven. He ran his hand along the lower spar cap. He could feel the rivet heads under the smooth aluminum skin, 1.5 inches apart, 42 rivets in a 24-inch section. He pulled out a pocket knife and gently tapped the blade against the skin between two rivets. The metal was tight. It didn't resonate. It didn't ring. It was locked down, clamped between two rows of rivets like a piece of metal in a vise. He thought about the flak burst, the concussion wave hitting that wing, the force trying to bend the spar. And he thought about what happens to metal when it can't flex. It cracks. He had seen it 1,000 times in Detroit, over-riveted joints in car frames. They looked strong. They tested strong. But on the road, under real-world vibration and stress, they'd crack at the rivet line. Always at the rivet line. Piasecki made a decision. He wasn't going to argue with engineers anymore. He was going to prove it. He went to his tool locker and pulled out a 3-foot section of scrap aluminum spar left over from a rejected wing. It was the same alloy, the same dimensions as the B-24's main spar. He took it to his workbench. He drilled 2 sets of rivet holes. The first set was spaced at 1.5 inches, exactly to spec. The second set was spaced at 3 inches, twice the standard spacing. He drove rivets into both sections, attaching strips of aluminum sheet to simulate the wing skin. Then he took both sections outside to the scrapyard behind the factory. He clamped the first section, the tight riveted one, into a vise mounted on a steel workbench. He took a 5-pound sledgehammer and hit it. Hard. Once. Twice. On the third hit, the aluminum cracked. A hairline fracture appeared right along the rivet line. He pulled it out of the vise and examined it. The crack ran for 6 inches, following the rivets like a dotted line. He took the second section, the one with the wider rivet spacing, and clamped it in the same vise. He hit it. Same force. Same hammer. 5 times, 10 times, 15 times. No crack. Piasecki stood there in the dark scrapyard, holding that piece of aluminum, and he knew. He knew that every wing coming off the Consolidated assembly line was being built wrong, and he knew that the engineers would never believe him. Not without proof they couldn't ignore. He needed a test. A real test. With a real airplane. And he needed permission. But permission, in wartime, from a military bureaucracy 7 layers deep, would take months, if it came at all. So Piasecki did what desperate men do. He broke the rules. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The next morning, March 23rd, 1943, Frank Piasecki walked into the office of the plant manager, a man named Charles Lowell. Lowell was former Navy, a no-nonsense administrator who cared about one thing: production numbers. Piasecki laid out his theory: the tight rivet spacing, the lack of flex, the cracks. Lowell listened, his face unreadable. When Piasecki finished, Lowell leaned back in his chair. If you're wrong, if we modify a wing and it fails, what happens? Piasecki didn't hesitate. Men die, sir, and I get court-martialed. Lowell stared at him for a long moment. Then he made a decision that probably saved his career, or ended it, depending on how the test went. He picked up his phone and called the military liaison officer at the plant. He told him that Consolidated was going to conduct an unauthorized structural test on 1B-24, tail number 4251773, and that if anyone from the Army Air Force wanted to stop him, they'd better do it in the next 6 hours, because after that, the wing was being modified. The liaison officer, a lieutenant colonel named Richard Bates, arrived at Lowell's office 30 minutes later. He demanded an explanation. Lowell handed him Piasecki's test sections, the cracked spar and the flexed spar. Bates examined them. He wasn't an engineer, but he understood the implications. He made a phone call to Wright Field in Ohio, the Army Air Force's testing center. He explained the situation. The officer on the other end told him to stand by. 2 hours later, Bates received a telegram. It was from Major General Oliver Eccles, head of the Air Force Materiel Command. The message was short: proceed with test. If successful, implement immediately. If failure, court-martial will follow. That was it. No formal approval, no engineering review. Just a green light and a threat. Piasecki had 48 hours to prove his theory or face prison. Piasecki assembled a team, not engineers, mechanics, men he trusted. Men who knew how to work fast and keep their mouths shut. There were 5 of them. Tommy Rodriguez from Los Angeles, a sheet metal worker. Carl Jensen from Minnesota, a rivet bucker. James Hawkins from Texas, a structures man. And 2 brothers, Eddie and Frank Kowalski, both riveters from Chicago. They met in the far corner of the assembly hangar at 2300 hours on March 23rd. The plant was mostly empty. The night shift was working in another building. Piasecki had already selected the aircraft. B-24D, tail number 425173. It was a brand new Liberator, fresh off the line, not yet delivered to the Army. It sat on jacks in the final inspection bay, its wings still unpainted, bare aluminum gleaming under the overhead work lights. Piasecki gathered his crew around the right wing. He explained what they were going to do. They were going to remove every other rivet from the lower spar cap. They were going to double the spacing from 1.5 inches to 3 inches. They were going to do it without damaging the surrounding structure. And they were going to do it in one night. Rodriguez asked the question they were all thinking. "Frank, if this doesn't work, we're all going to Leavenworth, right?" Piasecki nodded. "That's right. So let's make damn sure it works." They started at midnight. The first step was to drill out the rivets. Not all of them. Every other one. The pattern had to be precise. If they removed the wrong rivets, the wing could fail immediately, right there on the jacks. Rodriguez worked with a pneumatic drill, a high-speed bit designed for aluminum. He positioned the bit exactly on the center of the rivet head, applied pressure, and squeezed the trigger. The drill screamed. Aluminum shavings spiraled away. The rivet head disappeared. He punched the shank out with a drift pin. One rivet removed. 41 to go in this section. Each rivet took 90 seconds. Do the math. 41 rivets, 90 seconds each. 62 minutes just to drill out one side of one spar section. And they had to do both wings, both spar caps, 4 sections total. The clock was ticking. Jensen and the Kowalski brothers worked the left wing simultaneously. Hawkins was the inspector. After every rivet was removed, he'd check the hole. If it was damaged, if the drill had wallowed out the aluminum, the whole joint would be compromised. Every hole had to be perfect. By 0300 hours, they'd removed 84 rivets from the right wing. Piasecki examined the spar. He ran his hand along the lower cap. It felt different already. Looser. The metal had a slight give to it now. He pressed down on the wing skin between 2 remaining rivets. It flexed. Just a fraction of an inch. But it moved. That was what he wanted. That tiny bit of movement, that microscopic ability to absorb shock instead of transmitting it rigidly into the structure. That was the difference between a wing that cracked and a wing that survived. By 0530, the job was done. 168 rivets removed. The wing still looked solid. The remaining rivets, now spaced 3 inches apart, were carrying the load. Piasecki stood back and looked at his work. It looked wrong. It looked weak. Every instinct, every regulation, every engineering manual said, you don't remove rivets from a primary structure. You add them. But Piasecki's 20 years of experience building stressed metal structures said otherwise. He cleaned up the drill shavings, packed his tools, and sent his crew home. He told them not to come to work the next day. If the test failed, if the wing folded on the ground or in the air, he didn't want them anywhere near the plant when the investigators arrived. At 0600 hours, the day shift arrived. The test pilot, a civilian contractor named Ray Maguire, walked into the hangar. Maguire was 42 years old, a former barnstormer who'd been testing aircraft for Consolidated since 1940. He'd flown every variant of the B-24. He knew the airplane better than the engineers who designed it. Piasecki met him at the aircraft. Maguire looked at the Liberator, then at Piasecki. "This the one?" Piasecki nodded. "This is it." Maguire walked around the aircraft slowly. He didn't know what had been done to it. Piasecki hadn't told him. The plant manager, Lowell, had decided it was better that way. If Maguire knew the wing had been structurally modified, he might refuse to fly it. And they needed an unbiased test. Maguire completed his walk-around. Everything looked normal. He climbed into the cockpit. Piasecki watched from the hangar floor, his stomach twisted in knots. At 0715, Maguire started the engines. All 4 Pratt & Whitney R 1830 Twin Wasps roared to life. The sound was deafening, a physical force that vibrated the concrete floor. Maguire ran through his checks. Oil pressure, fuel flow, magnetos, hydraulics, everything green. He released the brakes. The B-24 rolled forward, out of the hangar, into the pale morning light. Piasecki, Lowell, and Colonel Bates followed in a jeep. They drove to the edge of the runway and stopped. Maguire taxied into position. The tower gave him clearance. The 4 engines roared to full power. The bomber accelerated down the runway, faster, faster, and then lifted off. Gear up, flaps up. The B-24 climbed into the California sky. The test plan was simple. Maguire would climb to 15,000 feet, level off, and then perform a series of increasingly violent maneuvers, steep turns, barrel rolls, and finally, a maneuver that no sane pilot would ever do in a fully loaded bomber, a split S from 15,000 feet, an inverted dive, pulling maximum G-force on the wings. If the wing was going to fail, it would fail during that maneuver. Piasecki stood on the tarmac, his eyes locked on the distant speck of the aircraft. He couldn't see details from this distance. He could only wait. 15 minutes passed. Then, through the binoculars, he saw it. The B-24 rolled, inverted at 15,000 feet. It hung there for a moment, upside down, and then the nose dropped. The aircraft entered a vertical dive. Piasecki stopped breathing. The bomber fell for 6,000 feet, the airspeed building, 300 miles per hour, 350, 400. The wings were under maximum negative load, the exact opposite of normal flight. The spar was being pulled upward, not down. The lower cap, the section where the cracks always started, was now in compression. At 9,000 feet, Maguire pulled. He hauled back on the control yoke with everything he had. The nose came up. The wings flexed visibly. You could see it even from the ground. The wingtips bent upward, the outer panels trailing behind the fuselage as the aircraft pulled out of the dive. 5 Gs, 6 Gs. The wings were bending, flexing, absorbing the load. And they held. The B-24 leveled off at 8,000 feet. Maguire flew straight and level for 30 seconds, checking his instruments. Then he climbed back to altitude and did it again. Another split S, another maximum G pull-out. The wings flexed, they held. He did it a third time. On the ground, Piasecki felt his knees go weak. It was working. The wing wasn't cracking. It was bending, absorbing the shock, and springing back. After 45 minutes, Maguire brought the aircraft back to the field. He landed, taxied to the hangar, and shut down the engines. Piasecki was there before the props stopped turning. Maguire climbed out of the cockpit, his flight suit soaked with sweat. He looked at Piasecki and said 2 words. "What do you do?" Piasecki told him. He explained the rivet spacing, the theory, the modification. Maguire listened, then walked to the wing. He ran his hand along the lower surface, feeling the rivet pattern. He looked at Piasecki with something close to awe. "Frank," he said, "that's the smartest stupid thing I've ever seen." Colonel Bates ordered an immediate inspection. A team of mechanics pulled the inspection panels off the wing. They examined the spar with magnifying glasses, looking for cracks, for any sign of failure. Nothing. The spar was perfect. The remaining rivets showed no signs of stress. The aluminum between the rivets had flexed, but it hadn't yielded. It had returned to its original shape. Bates made a phone call to Wright Field. He reported the results. The officer on the other end of the line was silent for a long moment. Then, "Do it again, tomorrow, with a fully loaded aircraft. Fuel, bombs, crew. If it works, we're modifying the fleet." He sat in his kitchen, drinking coffee, running the calculations in his head. A fully loaded B-24 weighed 60,000 pounds. Empty, it weighed 36,000. The additional weight would put significantly more stress on the spar during the pullout. If his theory was wrong, if the wider rivet spacing couldn't handle the load, the wing would fail, and Maguire, along with a volunteer crew, would die. The next morning, March 25th, Maguire took off in tail number 425173, fully loaded. 10,000 pounds of fuel, 5,000 pounds of practice bombs, a crew of 10 men, all volunteers who knew exactly what they were testing. They climbed to 15,000 feet. Maguire performed the same test sequence: steep turns, barrel rolls, split S dives, maximum G pullouts. The wings flexed, the aircraft shuddered, the rivets held. After an hour of punishing maneuvers that would have torn a standard B-24 apart, Maguire landed. The inspection revealed the same result. No cracks, no failures. Perfect. On March 27, 1943, the Army Air Force issued Emergency Technical Order 1943-16. Every B-24 Liberator in the inventory, every aircraft in production, would be modified. The rivet spacing on the lower spar cap would be changed from 1.5 inches to 3 inches. Existing aircraft would have every other rivet drilled out. New aircraft would be built to the new specification. The modification would be performed in the field by squadron maintenance crews. The technical order included detailed instructions written by Piasecki himself on exactly which rivets to remove and in what sequence. The order went out to every B-24 unit in the Army Air Force, the 8th Air Force in England, the 15th Air Force in Italy, the 5th and 13th Air Forces in the Pacific. Within 2 weeks, mechanics at air bases from East Anglia to Okinawa were drilling out rivets, following Piasecki's pattern. The pilots, the men who'd been flying coffins, noticed the difference immediately. The wings felt different. They flexed more in turbulence. Some pilots didn't like it. It felt wrong, unstable. But the wings stopped breaking. That was all that mattered. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The proof came in combat. The first modified B-24 to take battle damage was a Liberator from the 93rd Bomb Group, the same unit that had lost Lucky Strike. The aircraft, nicknamed Desert Rat, was hit by Flak over Wilhelmshaven, Germany, on April 4, 1943. An 88mm shell burst 30 feet below the right wing. The concussion wave hit the wing with the same force that had killed Lucky Strike 2 weeks earlier. The crew felt the impact. They felt the wing flex upward. The pilot, Lieutenant Thomas Hayes from Ohio, looked out at the wing, expecting to see it fold. Instead, he saw it bend, maybe 20 degrees, and then spring back. The wing held. Desert Rat completed the mission, dropped its bombs, and returned to base. The ground crew inspected the wing. They found shrapnel damage to the skin. They found 3 buckled ribs. But the spar, the critical structure, was intact. No cracks. Hayes filed a combat report. He described the flak hit, the wing flex, the survival. The report was forwarded to Wright Field. The engineers there compared it to the pre-modification data. A standard B-24, hit in the same location with the same force, would have lost the wing. The modification had saved the aircraft and 10 lives. The statistics over the next 6 months told the story. From April through September of 1943, the 8th Air Force flew 4,216 B-24 combat sorties. They encountered heavy flak on 62% of those missions. 387 aircraft took battle damage severe enough to require major repairs. 14 aircraft were lost to catastrophic wing failure, 14. Before the modification, in January through March, the loss rate from wing failure had been 47 aircraft in just 3 months. The modification had reduced the failure rate by 82%. By the end of 1943, over 2,200 B-24 Liberators had been modified. The Army Air Force estimated that Piasechi's rivet spacing change saved between 1,100 and 1,300 lives. 1,100 men who would have died, who went home instead. Some became fathers. Some became teachers. Some opened businesses. They lived full lives because a machinist from Detroit made their wings flex. But the story of the modification, the story of how it happened, was buried. The Army Air Force never publicly credited Frank Piasecki. The official technical order listed the modification as approved by Wright Field Engineering Division. No names, no details. Consolidated Aircraft didn't credit him either. The company's internal documents attributed the change to ongoing structural analysis. The engineers, the men with degrees who'd missed the problem entirely, received the credit. Piasecki's name appeared nowhere. There was a reason for this. The modification was an embarrassment. It proved that the original design, approved by the best aeronautical engineers in America, had been wrong. It proved that thousands of aircraft had been built with a fatal flaw, and it proved that the man who fixed it wasn't an engineer at all. He was a machinist who'd learned his trade building cars. The military, the corporation, they couldn't admit that, so they buried it. Piasecki didn't fight it. He wasn't looking for credit. He'd done what he'd done to save lives, not to make a name for himself. He continued working at Consolidated until the end of the war. He supervised wing assembly. He trained new workers. He watched B-24 seconds roll off the line, their wings now built to his specification, and he never told anyone that the modification was his idea. After the war, in 1946, Piasecki returned to Detroit. He went back to work for Ford Motor Company. He spent the next 23 years building cars, the same job he'd had before the war. He retired in 1969. He never spoke publicly about the B-24 wing modification. Not to reporters, not to historians, not even to his family, but the pilots, the men who flew the modified Liberators, some of them knew. They'd heard the stories. They'd heard about the machinist in San Diego who'd changed the rivet spacing. Some of them, after the war, tried to find him. In 1967, a group of B-24 veterans, members of the 2nd Air Division Association, tracked Piasecki down. They were organizing a reunion in San Diego. They wanted him to attend as their guest of honor. Piasecki declined. He told them he was just a mechanic. He said the real heroes were the men who flew the missions, who faced the Flak, who didn't come home. He didn't think he deserved recognition for doing his job. The veterans didn't give up. In 1973, they commissioned a plaque. It was mounted at the Air Force Museum at Wright-Patterson Air Force Base in Ohio. The plaque reads, "In memory of the innovation and courage of the aircraft maintenance personnel who modified the B-24 Liberator wing structure under combat conditions, saving countless lives." 1943 to 1945. Piasecki's name isn't on it. He would have wanted it that way. Frank Piasecki died in 1987. He was 82 years old. His obituary in the Detroit Free Press was 4 sentences long. It mentioned his work at Ford. It mentioned his service as a civilian contractor during the war. It didn't mention the B-24. It didn't mention the 1,100 lives he saved. But in the archives at Wright-Patterson, in the technical files on the B-24 Liberator, there's a folder. It contains the original Emergency Technical Order 1943-16. It contains test reports, inspection data, and combat damage assessments. And clipped to the inside cover of that folder is a handwritten note. It's dated April 1943. It's from Major General Oliver Eccles, the officer who authorized the test. The note reads, "The modification described herein was developed by civilian contractor Frank Piasecki, Machinist, Consolidated Aircraft, San Diego. Recommend personal commendation." The commendation never happened. The note was filed and forgotten, but it's there. It's proof. Proof that sometimes the most important innovations don't come from the men with the degrees and the titles. They come from the men with the wrenches and the common sense. The men who understand that engineering isn't just about making things stronger. Sometimes it's about making them smart enough to bend. The B-24 Liberator flew for the rest of the war. It dropped more bombs than any other American aircraft. It flew more combat missions than the B-17. And it brought more crews home alive, because one machinist understood something the engineers didn't. Metal doesn't have to be rigid to be strong. Sometimes the ability to flex, to absorb punishment and spring back, that's the greatest strength of all. In 1991, a mechanical engineering professor at MIT, Dr. Catherine Reynolds, was researching the history of aircraft structural design. She came across Emergency Technical Order 1943-16. She noticed something odd. The modification violated every accepted principle of aircraft structures. Reducing rivet density should weaken a joint, not strengthen it. She dug deeper. She found the test reports from March 1943. She found the combat damage data. And she found Eccles's note about Frank Piasecki. Dr. Reynolds wrote a paper. It was published in the Journal of Aircraft in 1993, 50 years after the modification. The paper was titled "Flexibility as Strength, the B-24 Wing Modification and the Limits of Rigid Design Philosophy." In it, she analyzed Piasecki's modification using modern finite element analysis and computer modeling. Her conclusion: Piasecki had been absolutely right. The tighter rivet spacing had created a stress concentration at the rivet line. The shock wave from a flak burst, instead of being distributed across the entire spar, was focused at the rivets. The aluminum between the rivets, locked rigid, couldn't absorb the energy. It could only crack. By spacing the rivets farther apart, Piasecki had allowed the metal to flex. The energy from the shock wave was absorbed by the elastic deformation of the aluminum, then released as the metal sprang back. The spar acted like a spring, not a rigid beam. It was, Dr. Reynolds wrote, a brilliant example of practical engineering intuition overcoming theoretical dogma. Her paper sparked a minor revolution in aerospace engineering education. Today, the B-24 wing modification is taught as a case study at MIT, Caltech, and the Air Force Academy. It's used to illustrate the importance of real-world testing, the value of hands-on experience, and the danger of relying too heavily on theoretical models. Engineering students are told about Frank Piasecki, the machinist with no degree who saved 1,100 lives, because he understood something the PhDs didn't. He understood that the real world doesn't always follow the textbook, and he had the courage to trust his instincts, even when every regulation, every expert, and every equation said he was wrong. That's the legacy. Not a medal, not a promotion, not even a mention in the history books. Just the knowledge that 1,100 men came home because one man was willing to break the rules to save them. Up next, you've got two more standout stories right on your screen. If this one hits the mark, you won't want to pass these up. Just click and check them out. And don't forget to like, subscribe and turn on the notification bell so you don't miss any upload from us.